Hey, so today we're going to be talking about quantum numbers and the rules associated with it as well as electron spin. So, first things first, we got to know what exactly we're talking about with quantum orbital theory, and it's different from Bohr's theory in this following way. Quantum orbital theory says that all of this space between the nucleus and the space outside of the nucleus is considered a space that an electron can be at any given time, given the duality of electron and the duality of the electron form, which is wave particle form. So it can be in any of these crevices in any of the space at any given time, which means we have to have a pretty complex way of deciding that this is exactly the space that we want it to be in. So we have 4 different quantum numbers that help us decide where exactly this electron is in space. So the first one we're talking about is principal quantum numbers, which we represent with n, and n can equal any integer 1, 2, 3, 4, 5, 6, 7, etc. This is particularly talking about the shell level and the distance from the nucleus. So if we have a nucleus here, this distance here could be 1, and this distance further would be 2, and then 3, etc., etc. So the further from the nucleus that we get, the larger the number that n is, and also we have a higher energy state. So that higher energy state tells us that further away, more energy involved in this electron. So, moving on from there, that's the principle, and we'll be using n as a value and a lot more coming up. So, angular momentum quantum numbers is represented with L, and L can equal 0, 1, 2, 3, all the way up to n minus 1. So, if you're looking at n, for instance, and n equals 1, then L has to equal 0. So it can be all the way up to n minus 1. And what L tells us is the shape of the orbital. So going up into this diagram here, we can see that we have multiple shapes. We have an s orbital, which gives us a sphere, a p orbitals, which give us like this dumbbell shape. So we have a sphere and like a dumbbell shape. And then d orbitals, which are a bit more complex. They're kind of like this dual form type thing. And then the f orbitals, which are even more complex, which I'm sure that makes sense. That electron, I'm not very good at drawing it, but that kind of atom theory that you're used to seeing. So those orbitals are shown in this diagram here, and it's a really nice diagram that points out all the different forms there. So with L, we know the shape. So if we're looking at like a sphere, then we're looking at an S, and then like I said, p orbital is like a dumbbell and so forth. So we're going to just work with these simple ones for now as we move forward. Now a couple things to note. This L here is in this equation, and this gives us this L here, which that L is the magnitude of the angular momentum. So that L can tell us a great deal about how much energy is associated inside this electron and moving around and everything. So now moving forward to the magnetic quantum number, it's ML, and I know that's hard to see with that. It looks like a 1. It's ML, so M subscript L. So that tells us about the orientation of the orbitals. So for instance, if we have just this plain old sphere, it's just going to be here in this singular plane. And so when we have the singular plane, it's pretty simple, and that would be something like a n equals 1 situation where L equals 0, because if you look here, we have L's right here that can tell us a lot. So, for instance, if L equals 0, that's 0 is 0, but if it's 0 and -1, so -1, 0, and 1 can tell us a whole lot about what we're dealing with. So, if we're looking at it and we have p orbitals, and we have the y, the x, and the z axis. If we're looking at p orbitals, they could either be on the z, right? So you have this p orbital there, or you could have a p orbital on the y-axis, like so, or you can have one on the x-axis, like so. And because you have those different orientations there, it's good to have a quantum number that'll tell you where that is, and that's m of L. Now, looking over here at this equation, there's m of L right there, and then this L of z, that currently is basically, it's the z coordinate. Let me redo that. The z coordinate of the angular momentum. So that's this portion up here, where it is. And I'll show you a diagram later that kind of helps with that. So on the fourth number here, as we move down, we're now talking about m of s, which is the spin. So it's a lot of spin, and spin's technical. It's not necessarily true. So if you think about it this way, it's easiest, but this isn't how it works. So if you're looking at the electron itself, you're saying it could spin clockwise or counterclockwise. It could rotate like a top, which isn't really how it goes, but that helps you understand that this s number is, so the negative would be like the counterclockwise, and the positive would be like the clockwise. Now you also have this s value, which is not to be confused with the m of s. This s value is different for electrons, neutrons, protons, and the m of s is based off of that s value. Now, if you take that s value, you could plug it into this equation right here to determine those two. And this s is, again, the magnitude. But this is the magnitude of the intrinsic spin. So that I believe what they call it, the magnitude of intrinsic spin angular momentum is what they call it. And then this one over here, the s of z, that one is the z coordinate again. And that is the z coordinate of the intrinsic spin momentum. They call it z component of spin angular momentum. So dealing specifically with the spin. So putting all those together, you can come up with a chart here, and it shows you here. So here's N and L, and then M of L, and then over here, the stuff to the left of this blue line that I draw, that is all pretty much chemistry terms. And so you're looking at orbitals, and then the names of the orbitals, and then the electrons in those orbitals. And remember, we're dealing with a wave particle form of electrons, so they are harder to pinpoint. So again, this chart is useful. If you look, N is 1, L has to be 0, and then M of L is 0. And then you can go down to 2, and you have 2 different options. You go down to 3, and you add a third option. You go to 4, you add a fourth option, and keep going and keep going. Now, looking on this right-hand side, this little diagram, you can actually determine angles of momentum and theta 1, 2, and 3 based on this graph here. Theta 1, 2, and 3. You can determine those because if you know L and you know LZ, and then if you know S or SZ in those situations, then you can determine where exactly away from the nucleus the electron is. Not necessarily determined exactly, but you can predict these. Because since it has the wave-particle duality, the closer you get to one, the further away you get from the other, and so forth. And so it's like, it's kind of a difficult thing to pinpoint. So using all these tools, you can come up with these And so let me go back through. Remember, we're dealing with a space that this shell occupies. Remember that n is the principal quantum number. It has a lot to do with the distance from the nucleus, and then the higher energy the further away, so how big the shell is and how far it is. Angular momentum has to do with the shape of the orbital, whether it's a p, s, d, or f orbital. And then remember that it can only be n minus 1 or lower. And then looking at the magnetic quantum number m of L, you're looking at the orientation of the orbitals, where on the z, y, and x axis it is. And with that, you have L of z, which can tell you the z coordinate. And then looking at the spin quantum number, remember that it's easiest to think of it as a spinning top, but it's not necessarily that way. You have another z coordinate with that spin and angular momentum. You have another magnitude as well to deal with that. And remember that s and m of s are different, and s varies depending on a nucleus, neutron, or proton. And with all that, then you can look at this chart, feel with confidence, know what these numbers all mean, and possibly even solve some problems.